Welcome to this walkthrough of LeetCode problem number 2096, step-by-step directions from a binary tree node to another. In this problem, we'll explore how to determine the shortest path between two nodes in a binary tree, represented with directional steps using U, L, and R. Let's dive in and break down the solution step by step. In this problem, you are working with a binary tree containing n nodes, where each node has a unique value ranging from 1 to n. You are given two specific values, called start value and dest value, which correspond to two different nodes in the tree. Your task is to determine the shortest path between these two nodes, and represent this path as a sequence of directions. The directions are encoded as a string using three uppercase letters, U4 moving up to the parent node, L4 moving to the left child, and R4 moving to the right child. The goal is to return this string of directions that outlines how to navigate the binary tree from the starting node to the destination node. To clarify the problem further, let's look at an example. Suppose the binary tree is structured as shown, with root equals 5 1 2 3 null 6 4, start value equals 3, and dest value equals 6. Here's the visual representation of the tree. The root node is 5, which has two children, 1 and 2. Node 1 has a left child, 3, while node 2 has two children, 6 and 4. In this case, the output should be the string URL, which represents the shortest path from node 3 to node 6. Now, let's break down the solution for this example. Starting at node 3, the first step is to move up to its parent, which is node 1. From there, move up again to the root node, 5. Next, move right to the child node 2, and finally, move left to reach node 6. Together, these steps form the path URL, which is the shortest sequence of directions from the starting node to the destination node. In another example, consider a simpler binary tree with root equals 2 1, start value equals 2, and dest value equals 1. Here, the root node is 2, and it has a single left child, 1. The output for this input is U. This is because the shortest path from node 2 to node 1 involves just one step, moving up to the parent node, which is node 1. For a third example, take a binary tree represented as root equals 1 null 10 8 null 7, with start value equals 8 and dest value equals 7. In this tree, the root node is 1, which has a right child, 10. Node 10, in turn, has two children, 8 on the left and 7 on the right. The output here is UR. Starting at node 8, the first step is to move up to its parent, node 10. Then, move right to reach node 7. These steps form the path UR. Finally, let's discuss some constraints and edge cases. The binary tree can have up to 100,000 nodes, with all node values guaranteed to be unique. The start value and dest value will always be different, and the tree is always a valid binary tree with no duplicate nodes or cycles. Special scenarios to consider include when the start value or dest value is the root itself, which might result in a path involving only upward or downward traversal. Additionally, ensure that your solution accounts for traversals across both the left and right subtrees when the nodes are on opposite sides of the root. To solve problem number 2096, the objective is to find the shortest path in a binary tree from a starting node to a destination node. The result should be a sequence of directions using U, L, and R, representing upward, leftward, and rightward moves, respectively. The brute force approach begins by identifying the paths from the root node to both the start node and the destination node. By comparing these two paths, we can determine the lowest common ancestor, or LCA, which is the point where the paths diverge. From the start node to the LCA, we calculate how many steps are needed upward, appending U for each step. Then, from the LCA to the destination node, we calculate the remaining path, appending L or R based on the direction taken in the binary tree. While this approach works with a time complexity of O(n), it involves redundant traversals of the tree to collect and compare paths, making it less efficient. An optimized approach addresses these inefficiencies by directly calculating the lowest common ancestor without fully collecting the paths. Once the LCA is identified, we can efficiently compute the directions. The steps include first implementing a helper function to find the LCA of the start and destination nodes. Then, we traverse upward from the starting node to the LCA, appending U for each step. After reaching the LCA, we traverse downward to the destination node, appending L or R based on the branch taken. This approach maintains a linear time complexity of O(n), but avoids redundant path collection, making it much cleaner and faster. The key insight here is that the LCA serves as a natural midpoint between the upward and downward traversals. By breaking the problem into two distinct parts, from the start to the LCA, and from the LCA to the destination, we streamline the solution. While this method requires careful implementation of the LCA function, it is efficient, minimizes tree traversals, and fully leverages the structure of the binary tree. In this problem, we are tasked with finding the shortest path between two nodes in a binary tree using specific movement directions. These directions are represented by U4 moving up to the parent node, L4 moving to the left child, and R4 moving to the right child. The goal is to compute the path string efficiently, given the root of the tree, the starting node value, and the destination node value. To achieve this, the algorithm begins by identifying a critical point of reference, the lowest common ancestor, or LCA. The LCA is the lowest node in the tree that is an ancestor of both the starting node and the destination node, acting as a natural meeting point for their paths. To locate the LCA, we use a recursive depth-first search, or DFS, which explores the tree systematically. If the current node is null, we return null. If the current node matches either the starting or destination value, we return the node itself. Then, by recurring on both the left and right subtrees, we identify whether the LCA lies in either path. If both sides return non-null results, the current node is the LCA. Otherwise, the search continues, returning the non-null child if only one side contains the node. This process ensures we can locate the LCA in n time, where n is the number of nodes in the tree. Once we have the LCA, the next step is to determine the path from the starting node to the LCA. This allows us to compute the number of U steps needed to move upward. To achieve this, we perform another DFS starting from the LCA, tracking the path as we go. If we encounter a node that matches the starting value, we stop the recursion and return the path as a sequence of U steps. Next, we focus on the path from the LCA to the destination node. This downward path will consist of L and R steps, corresponding to left and right child movements. Again, we use a DFS from the LCA, keeping track of the path in a string or list. When we reach the destination node, we stop the recursion and return the path. The final step is to combine these two results. The upward path of U steps and the downward path of L and R steps naturally merge to form the complete path string. This step-by-step approach ensures clarity and efficiency when solving the problem. Breaking the problem into these steps highlights several key insights. First, the LCA serves as an intuitive meeting point, simplifying the process of finding the shortest path. By splitting the task at this node, we reduce the complexity of the traversal. Additionally, using DFS for tree traversal is highly effective, as it allows us to explore paths recursively and backtrack only when necessary. This approach takes advantage of the tree's structure, where upward and downward paths complement each other symmetrically. To implement the solution, we rely on standard data structures. The binary tree is represented using nodes with val, left, and right properties. For path tracking, string builders or lists are appropriate tools to store the sequence of movements during traversal. It's important to consider edge cases as well. For example, if the tree consists of only a single node and the start and destination values are the same, the result is simply an empty string. Unbalanced trees, which have uneven heights, are handled seamlessly as long as the nodes exist. Finally, while the problem assumes valid inputs, you may choose to add checks to verify the presence of both nodes in the tree. Analyzing the complexity of this algorithm, the time complexity is O(n), where n is the total number of nodes in the tree. This accounts for the DFS to find the LCA and the subsequent traversals to trace the paths. The path traversal steps are proportional to the height of the tree, denoted as h, making their time complexity O(h). For space complexity, the primary consideration is the recursion stack used during the DFS, which also scales with the height of the tree. Thus, the space complexity is O(h). This balance between time and space efficiency ensures the algorithm can handle binary trees of varying sizes effectively. To solve this problem, we start by defining the getDirections method within the solution class. This method will ultimately compute the step-by-step directions from one node to another in a binary tree. First, we define a helper function called findPath, which is responsible for finding the path from the root node to a specific target node. The function uses recursion to traverse the tree. If the current node matches the target, it returns true, signaling that the path has been found. Otherwise, it explores the left and right subtrees. If the left subtree is explored, we append L to the path to indicate moving left, and if the recursive call succeeds, we return true. If not, we backtrack by removing the last step using path.pop. Similarly, we handle the right subtree by appending R, attempting the recursive call, and backtracking if necessary. This helper function ensures we can trace the exact path to any given node efficiently. Next, we define another helper function, findLCA, which is used to find the lowest common ancestor, or LCA, of two nodes. The LCA is the deepest node in the tree that is an ancestor of both target nodes. If the current node is null or matches one of the targets, we return the node itself as it may be the LCA. The findLCA function continues by recursively searching for the LCA in both the left and right subtrees. If results are found in both subtrees, it means the current node is the LCA, so we return it. Otherwise, we return whichever subtree contains a result, which will propagate up the tree to identify the LCA. Once we have the LCA, the first step in our main function is to compute it by calling findLCA with the root, start value, and dest value. The next step is to determine the paths from the LCA to each of the target nodes. We initialize empty lists for start path and dest path, then use the findPath function to populate these lists with the steps required to reach start value and dest value from the LCA. Finally, we generate the directions string. For every step required to travel up from start value to the LCA, we append a U to the result. Then, we append the steps in dest path to complete the path to dest value. The result is a string representing the full set of directions, which we return as the output of the function. Here, we begin by defining the method getDirections, which is responsible for finding the step-by-step path between two nodes in a binary tree. The method takes three arguments: the root of the tree, the starting node value, and the destination node value. First, we declare two lists, start path and dest path, which will store the directions from the lowest common ancestor, or LCA, to the start and destination nodes, respectively. Next, we call a helper method findLCA to determine the LCA of the two nodes. Once we have the LCA, we use another helper method, findPath, to fill the start path and dest path lists with the directions from the LCA to the respective nodes. To construct the final result, we append a series of U characters representing the steps from the starting node back up to the LCA, followed by the directions from the LCA to the destination node. Finally, we return the constructed path as a string. The findPath method is a recursive helper function that identifies the path from the current node to the target value. It takes three parameters: the current tree node, the target value, and the list to store the path. If the current node is null, it returns false, indicating that the path does not exist. If the current node matches the target value, it returns true, signaling that the target has been found. Otherwise, the method explores the left and right subtrees. If moving to the left child is successful, it adds L to the path, and if not, it backtracks by removing the last entry. Similarly, it adds R when moving right and backtracks if this path also fails. The method ultimately returns true if either subtree leads to the target node, ensuring that the path list is correctly populated with the necessary directions. The findLCA method is a recursive function used to determine the lowest common ancestor of two given nodes, P and Q. If the current node is null or matches one of the target values, it returns the current node as a potential LCA. Otherwise, it recursively searches the left and right subtrees for the two nodes. If both the left and right recursive calls return non-null values, it means one node was found in each subtree, making the current node their LCA. If only one of the recursive calls returns a non-null value, that means both nodes are located in the same subtree, so the LCA must be in that direction. Finally, the class also includes the definition for the tree node structure, which contains fields for the node's value and its left and right children. This structure forms the foundation for constructing and traversing the binary tree. In this example, we are given a binary tree with the root node 5 and two target nodes, start value 1 and dest value 6. The first step is to find their lowest common ancestor, or LCA. Starting at the root, we observe that both 1 and 6 exist in the left and right subtrees of node 5. Since 5 is the lowest node where both targets are found in separate subtrees, it is the LCA. Next, we determine the path from the LCA, node 5, to the start value, which is 1. From node 5, we move left to reach node 1, so the path to start value is represented as L. Now, we proceed to find the path from the LCA, which is node 5, to the dest value, node 6. Starting at node 5, we move right to node 2, and then continue right to node 6. This gives us the path to dest value as R. To generate the directions from start value to dest value, we first move up to the LCA by converting the path to start value into U. After reaching the LCA, we append the path to dest value, resulting in the combined directions U, R. Translating this to a string, the output is URR. In this second example, we are given a different tree with root node 3, and the start value is 5 while the dest value is 8. To find their LCA, we start at the root node 3. Both 5 and 8 exist in the left and right subtrees of node 3, making it the LCA. Next, we determine the path from the LCA, node 3, to the start value, 5. From node 3, we move left to reach node 5, so the path to start value is L. Similarly, to find the path from the LCA to dest value, node 8, we move right to node 1 and then right again to node 8, resulting in the path R. Combining these, the directions from start value to dest value are U, R, or URR. In the third example, the binary tree has root node 1, and the target nodes are start value 4 and dest value 5. To find their LCA, we begin at the root. Both nodes 4 and 5 exist in the left subtree of node 1, so we move to node 2. Here, both 4 and 5 exist in node 2 subtrees, making node 2 the LCA. Now, we determine the path from the LCA, node 2, to the start value, node 4. To find the path to start value, node 4, we start at node 2 and move left, resulting in L. Next, we find the path from node 2 to dest value, node 5, by moving right, giving us R. To generate the directions from start value to dest value, we first move up to the LCA by converting the path to start value to U. After reaching the LCA, we append the path to dest value, resulting in U, R. This gives the final output as UR. In analyzing the time complexity of our solution, we can break it down into 3 key steps. First, the process of finding the lowest common ancestor, or LCA, involves traversing the binary tree to locate the node where the paths to start value and dest value converge. This traversal requires visiting each node in the worst-case scenario, which gives us a time complexity of O(n), where n represents the total number of nodes in the tree. Next, the function findPath is used to determine the path from the LCA to each of the target nodes. Since this function is called twice, once for start value and once for dest value, and each call explores nodes along the height of the tree, the total contribution from this step is O(h), which simplifies to O(h). After finding the paths, the next step is to combine the results to generate the final path from start value to dest value. This involves concatenating the paths, which takes p time, where p is the length of the resulting path. In the worst case, the path length p is proportional to the height of the tree, h, so this step also contributes O(h) to the overall complexity. Summing these components, we get O(n) for finding the LCA, O(h) for finding the paths, and O(h) for combining the results. Since the height of the tree h is at most proportional to n in a skewed tree, the total time complexity simplifies to O(n). Now let's consider the space complexity of the solution. Both the findLCA and findPath functions use recursion, and the maximum depth of recursion is determined by the height of the tree, h. In the worst case, such as in a skewed tree, this recursion depth becomes O(n). Additionally, we store the paths from the LCA to start value and dest value in 2 separate lists. The maximum size of each list is proportional to the height of the tree, h, which gives a combined storage requirement of O(h). Therefore, the total space complexity is dominated by the larger of these 2 contributions, the recursive stack space and the path storage. Both are O(h), which in the worst case simplifies to O(n). To better understand performance, let's examine the best, average, and worst case scenarios. In the best case, the tree is balanced, and the nodes start value and dest value are close to the root. Even in this scenario, we still need to traverse the tree to find the LCA, resulting in a time complexity of O(n). The space complexity remains O(h) due to the recursive stack and path storage. In the average case, the tree is roughly balanced, and the nodes are located at intermediate depths. Here, the time complexity remains O(n), and the space complexity is O(h). Finally, in the worst case, the tree is skewed, and the nodes are at the deepest level. This scenario results in both time and space complexities of O(n). When comparing our optimized solution to a naive approach, we see that both approaches achieve the same asymptotic time and space complexities, but the optimized solution is more efficient in practice. A naive approach might involve finding the paths from the root to both start value and dest value directly and then comparing these paths to determine the LCA. This requires finding the path to each node, which takes O(n) time per node, and comparing the paths, which adds another O(n). The total time complexity for the naive approach is therefore O(2n plus n), which simplifies to O(n). Similarly, the space complexity involves storing both paths and the recursive stack, which totals O(n). The optimized solution introduces several improvements. By first finding the LCA, it avoids redundant traversals of the same branches of the tree. This makes the process cleaner and more efficient overall. Additionally, the logical separation of concerns, computing the LCA first and then finding the paths, enhances code readability. Despite these improvements, the optimized solution still maintains the same asymptotic time and space complexities as the naive approach, ensuring that it is both efficient and easy to understand. When tackling this problem, there are several common mistakes to watch out for. One of the most frequent errors is failing to identify the lowest common ancestor, or LCA, of the two nodes. The LCA is critical because it acts as the junction point that divides the path into two distinct segments, the path from the starting node to the LCA, and then from the LCA to the destination node. Without correctly identifying this, the entire solution can fall apart. Another common issue is mishandling edge cases. For instance, if either the starting or destination node happens to be the root of the tree, or if the two nodes are directly connected, like in a parent-child relationship, your solution must account for these scenarios. Inefficient path reconstruction is another pitfall, where multiple tree traversals are used to build the path unnecessarily. Instead, aim to solve this with a single traversal to save time. Additionally, it's easy to confuse the directional symbols U, L, and R, which represent up, left, and right. Misusing these can lead to incorrect results, so double-check this logic during debugging. Lastly, if you're working with large trees containing thousands of nodes, using a brute force approach can result in time limit exceeded errors. Efficient algorithms like depth-first search or breadth-first search are key to handling these cases within the time constraints. Now, let's consider what's important when approaching this type of problem in an interview setting. A strong understanding of the lowest common ancestor concept is essential, as many binary tree problems rely on it. Be ready to explain the theory behind it and how it applies to this problem. Time complexity is another crucial discussion point. Highlight that this problem can be solved in O(n) time, where n is the number of nodes in the tree. This efficiency is achieved by traversing the tree just once. You should also be prepared to discuss tree traversal techniques, such as using DFS or BFS, to locate nodes and build paths. Testing edge cases is another area interviewers often focus on, so make sure you address scenarios where the starting and destination nodes are the same, or when one of them is the root. Lastly, it's important to clearly explain how the directions, represented by U, L, and R, are constructed from the traversal. To deepen your understanding, you can explore related problems like LeetCode 236, which introduces the concept of finding the LCA, or LeetCode 1123, which focuses on the LCA of nodes at the deepest level. Other problems like LeetCode 863 and 742 involve node-to-node traversal and pathfinding in binary trees, making them excellent practice. There are also alternative approaches to solving this problem, each with its own trade-offs. One option is the two-pass DFS method. In the first pass, you identify the LCA of the two nodes. Then, in a second pass, you compute the paths from the starting node and the destination node to the LCA. This approach is conceptually simple and straightforward to implement, but because it requires traversing the tree twice, it's less efficient. Another method is a single-pass DFS with backtracking. Here, you traverse the tree just once, while simultaneously determining the paths to both the starting and destination nodes. This reduces redundancy and improves efficiency, but it can be more challenging to implement due to the added complexity of managing the backtracking logic. A third approach involves using BFS with parent pointers. In this method, you use a BFS traversal to map parent pointers for each node, which allows you to later reconstruct the path. While this method can be effective, its trade-offs include additional space usage for the parent pointer map and the need to handle extra bookkeeping. Each of these approaches has its strengths and weaknesses, so the choice will depend on the specific constraints and priorities of the problem you're solving. Great job making it to the end. To summarize, we tackled the problem using the lowest common ancestor to determine the shortest path, combining upward and downward moves. Along the way, we reinforced key concepts like tree traversal and path construction. Don't forget to practice similar problems to strengthen your understanding. Thanks for watching, and see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!